Okay, so today we're going to move on into chapter 11. Chapter 11 is going to be about intermolecular forces. And the first part about intermolecular forces is you have to be able to do your molecular shapes. To do your molecular shapes, you have to be able to do your Lewis structures. So you want to make sure that you feel comfortable with that. And the reason why this is so important is because of polarity. And so in the beginning part of this, we have a couple warm-up questions where we're looking at molecular shapes. So C2Cl, that should be sorry, I made too many here. There we go. So we should have a triple bond between there. And so when we're looking at this picture, we should be able to determine our molecular shape. And so in this case, that should be linear. And we can tell that because each of those carbons is going to have a 2-electron region, no lone pairs. And so we can get our shapes that way. If we had changed that to CO, CO2, then we should have our carbon in the middle, chlorine, chlorine, double bond. Now we have 3 electron regions, no lone pairs, and so our molecular shape should be trigonal planar. Now, if we have 4 regions, which of these are a possibility for our molecular shapes? We should have the answer as all of these. A tetrahedral is when there's no lone pairs. Pyramidal, right, or trigonal pyramidal is going to be when there's 1 lone pair, and bent is going to be if there's 2 lone pairs. So you're right, this shouldn't be just pyramidal, this should be trigonal pyramidal. And so H2O has a bent shape, and SO2 also has a bent shape. And so we're trying to get an idea about what's the difference between those and how their bond angles would compare. So when we look at this, H2O should be HOH, 2 lone pairs on our oxygen, and SO2 is going to be SOO. We actually have 2 double bonds here. 10, 12, 14, 16, and 1 lone pair on our S. So both of them are going to be bent. But the difference here is about what geometries they started with. This one started from a tetrahedral. And so that H bond started off close to 109.5. On the other hand, our SO2 started off as a trigonal planar. And so it started off at an angle much closer to 120. And so our answer that we should be looking for is D, because they start off from different geometries. So even though they both end up with the same name, the angles are different between them because one started off from a 4-electron region, the other one started off from a 3. And so we want all of this because we want to be able to predict whether your molecule is going to be polar or not. So this is an example of where we can think about our polarity. So each one of these is starting off with our carbon in the middle, surrounded by 4 atoms. So we have carbon H, H, sorry, H, F. We have carbon H, H, F, F. And we have carbon F, 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 F. Now remember that these thicker ones, those are the ones coming out of the screen towards you. The ones that are dashed are going back into the wall, and the other ones that are just lines are in the same plane as the screen. So if we imagine this, we do know that between carbon and fluorine, those electronegativities there is a difference there. Carbon is not as electronegative as fluorine. So let's see the F bond. If we actually do the math, C is 2.4, F is 4.0. We have a difference there of 1.6. And so we should point from the, sorry, not 2.4, it should be 2.5. So we should point from that carbon towards that fluorine. The difference between carbon and hydrogen is 2.1, and so that's a difference of 0.4, and it's actually they're considered to be non-polar, so we don't have to draw them. But when we're looking to see if these molecules are polar or not, we're looking to see if they're balanced or imbalanced in these dipoles or in these bond polarities. So if something's imbalanced, it's going to be polar. If it's something balanced, then it's going to be non-polar. And so if we look at these arrows, we want to see if they cancel out. So on the far left, we only have one arrow. And so this fluorine is pulling down and to the left, and there's no other bond poles pulling in the opposite direction. So this is definitely going to be polar because it's imbalanced. That means that we're going to build up some amount of negative charge here with the electron spending more time with the fluorine, and we're going to build up some amount of positive charge on the opposite side because they're not evenly sharing them. Now, if we look at the one in the middle, we're going to look at the one on the far side. That's kind of the next easier one. And we can see that each of those bonds is kind of being offset by the other side. So this one that's pulling up, it's pulling directly up, and then these other fluorines are pulling down away from it to counter it. This one that's pulling to the right is directly countered by the one that's pulling to the left. So because all of these are evenly spread out and they all have the same strength, this is going to be considered to be a non-polar molecule, even though it has polar bonds. All of its electron densities, how they're spread out, are going to balance each other out. As one side becomes negative, the other side is going to become negative as well. And so we don't build up a negative and positive side because of the way that the bonds are pulling in opposite directions. This one in the middle, though, this CH2F2, when we first look at it, we might think, oh, it should be nonpolar because they kind of pull off in different directions. But together, both of these are below this carbon. So both of them pull in this downward manner. There's no other pull going upwards to counterbalance them. And so while they don't both pull in the left direction or don't both pull in the right direction, they do both pull down. And so this one is going to be polar because it's going to be imbalanced. Now, the reason why all of this matters for us is today we're talking about intermolecular attractions. So we're talking about why are molecules attracted to other molecules. So we know that within the molecule, we have those bonds that form covalent bonds, ionic bonds, metallic bonds. But now we're talking about the attraction between the particles of a substance. And this is important because it's related to the state that the matter takes on. So things that are attracted to each other moderately at room temperature or are strong, those become our solids and our liquids. Things that have weak attractions to each other, they become our gases. So the stronger the attraction, the higher the boiling point is going to be, and the higher the melting point of the solids. So really, the stronger their attraction, the more those molecules are going to be stuck together. And that means we have to put in more and more heat in order to separate them. Those molecules need to vibrate around, move around more before they can break away from the other molecules. So intermolecular attractions can be due to a couple of different attractive forces. Primarily, they have to deal with our positives and our negative charges. So intermolecular attractions, they can occur from a positive ion and a negative ion. So our cations and our anions. And so this is our ionic compounds. In some ways, we don't really think of them as being molecules being attracted because ions aren't really making up molecules. They're making up those ionic salts, so those crystal lattices. But we can think of them as what's holding the different ions together is that positive to negative one. Now, when things are polar, it means that they started to form a partial positive side and a partial negative side. So they're similar to the ion, but now they have just a slightly positive end and a slightly negative end. And so that's going to be one way that we have those attractions. The last one is going to be how our nonpolar molecules kind of stick together. And so we'll talk about that in a little bit. And so the stronger these attractions, then the more those molecules will hold on to each other. And so there's a couple things that we see, just like Coulomb's law, is that the larger the charge, then the stronger the attraction. And the longer the distance, the weaker the attraction is. So as we go through and we classify these things, you want to be ranking them as, well, is this increasing the charge strength? Is that why we are stronger or weaker? Are we farther apart? Is that why our intermolecular force might be stronger or weaker? Now, overall, these intermolecular forces are going to be much, much smaller than our bonds. So those covalent bonds, those ionic bonds between the atoms are going to be much stronger than these intermolecular forces. Now, the strength of attraction force, it gives us our different states. And while no particle is completely locked into place, the stronger the attractive force, the more they resist moving. And so that's why the stronger the attractive force, then we take on that solid state where our particles are really locked into their position and they can only vibrate around. The more moderate ones, they become our liquids because they can kind of move, but they have to get, but they can't just move freely. And then our gases are our weakest attractions because they can move freely between them. And so that's how our freedom is related, or our states are related to our intermolecular forces. It's about their freedom to move or not. The weaker their force, the more they can move around, the more they are like a gas. The stronger their force, then the more that they're going to be like a solid. So our solids are really packed in there. They can be set up in their regular order, or they can be kind of no arrangement to them in the longer scheme, but they're packed close together. And so that means that we can't really compress them anymore. It also means that they can hold on to their shape, so they don't need a container to hold on to their shape. And so what's going on with those atoms or those molecules inside is they just vibrate. So they stay in their positions and then they vibrate around. An example of a crystalline solid would be something like salts or diamonds, where they have like a geometric arrangement. So it's going to repeat itself over and over again. If you ever look at salt crystals, you'll notice that your salt crystals are almost always cubic in their shape. Whether the big crystals or small crystals, they always look that cubic because that sodium and that chloride inside your salt crystals are repeating over and over again. They have an ordered structure. Something that's amorphic is kind of like our plastics, our glasses, our carbons. They don't always take on that same shape. And so that's why they don't always have the same look if we look at them under the microscope. Our liquids are kind of that in between. They're kind of closely packed, so we can't really condense them down very much. Their volume stays constant, but they can move within each other, right? They can hold together as a material, but they can flow in their shape. And so they take on the shape of their containers. They don't have enough freedom to escape or expand to fill the container. So they still have to all be connected in that same like density, but they can move around and reorient their shapes. But they do stay connected together. And so that's why if you pour water onto a table, it will stay together as a puddle. It doesn't just completely separate away, but it can take on its shape depending on what container we pour it on. Gases, on the other hand, are completely different. They take on the container of everything that are, they take on the volume of the container that you put them in. So if you blow into an empty container, your gas that you just exhaled is going to fill that entire container. It's not going to stay segregated away. And so our gases have that the most freedom there. So our gases are our lowest force, our liquids are the middle, and our solids are the most. So the reason why we're interested in this is that we're interested in their attractive forces between them. So we're going to talk about the different attractive forces first, and then we're going to move on to that next part. And so there's a couple of different ones. So we have what we call dispersion forces, which I'm going to give you an alternative name for it, dipole-dipole attractions, and then hydrogen bonds. Those are going to be the three that we talk about. And these are the ones that hold our molecules together. So these are the ones for our covalent molecules. So the first one we're going to talk about is our weakest one, and it's called London forces. Your book can also call them dispersion forces. I don't like dispersion forces as much because it kind of implies that they're kind of pushing each other away, is the way I kind of feel like when you say that something disperses. But their full names are like London dispersion forces. And so you can call them London forces. I will also accept dispersion forces. And the reason why this happens is this happens in all molecules where you have electrons. And since all molecules have electrons, then all molecules have London forces. Now, these are our weak forces, and it's because our electrons are in motion. So when we have the electrons spread out inside of the atom, they might be evenly spread out, looking like this. But as they move around, those electrons can move independently of one another. And so they might move so that instead of being evenly split, we have just a little bit more electrons on one side than on the other. When that happens, we get this partial negative charge on that side compared to the partial positive on the other. Now, that might only last for a moment because those electrons can continue to move, so they might go back to being neutral, or they might even go down to this bottom one and have a different shift in their polarities. So London forces are caused because the electrons are shifting and moving around. Now, by themselves, they're pretty weak, but they can become much larger and more important as you get to larger and larger molecules. If you kind of imagine it, if this was our cell, or not a cell, our atom, and we have only one electron, that electron is going to shift that partial positive and partial negative from one side to the other as it moves around. Now, the most that could ever shift it is by one electron charge. If I have 100 electrons, it's unlikely that all 100 might be on the same side. But if it did get to that point, then we can now fit all 100 electrons onto one side, and that partial negative or partial positive would be a lot bigger compared to the just one electron. So the more electrons we have moving around, the bigger those swings can be. It's probably never going to be all 100 electrons out of the 100 are on one side, but maybe it's only 10. Maybe it is, an extra 10. Maybe it's an extra 20, right? So the more electrons we have there, the bigger those swings can be because there's more electrons in motion. And so we can have it shift one way or the other. Now, the reason why this is so important is that when we have them next to each other, our molecules, if this middle molecule builds a London force, so that means that it's got just a little bit extra electron on one side than the other, it's going to make a partial negative. Well, if this molecule gets that partial negative, then the one to its left is going to have to respond. As that negative charge comes over there, it's going to push these electrons away, and so that's going to shift over. And so it's going to create a partial negative in there, and it's going to create a partial positive on that other side. Now that partial positive is going to allow some attraction to occur between these molecules for that moment. We see the opposite on the right-hand side. This part became positive, so it's going to attract over electrons. Those electrons are going to make this one partially negative. And so we're going to build some attraction between those three molecules. Now, that's temporary because those electrons can still move around. And so then when those electrons in the center one move back to a neutral position, then these forces will move away. And so London forces are just a temporary situation. They come because the electrons are in motion, and we see them in all molecules where there are electrons. Now, this symbol here, what they're trying to show you is that instead of just being some, it's showing you that it's a very small amount. If we have one of those, then this is a partial charge. This one is saying that we have a partial of a partial, so even smaller. This is more related to our dipole, where we might have a polar molecule, and so it's going to have some movement of its charge, but not a complete moving of the electron. The partial is for our London forces, because those are just temporary, and so it's an even smaller amount. And then we use positive or negative charges when we have ions, because we have a complete extra electron, or we're completely missing that other electron. And so that's what that symbol stands for. So London forces, they are the primary way that our nonpolar molecules interact. This means that those nonpolar substances have our weakest attracted or intermolecular forces generally. So I'm going to use IMF as intermolecular force. And so they typically have our lowest boiling point or melting point. Right? So they're our weakest force. So when we talk about melting points and boiling points, the reason why this is related to your attraction is that all of our molecules are in motion. And so they're moving around and moving around. And so their state of matter depends on how much energy they have as they move and the attraction between the particles. So as our temperature heats up, then we get, sorry, wrong slide. As our temperature heats up, we increase the kinetic energy. The more energy they have, then the more freedom they can have. Now, as our temperature increases, we can eventually overcome those attractive forces holding those molecules together. Gases have a weaker attractive force than our solids, than our liquids. And so as we increase our temperature, then we're eventually going to try to transition from one state to the next. So when our kinetic energy is significantly larger than our attractive force, we can see a change in our state. We could go from being a solid to being a liquid, say, and we would melt. When we add in even more energy, we might become even larger compared to those attractive forces, and we might become a gas. And so those state changes are all related to that attractive force holding them together. So if we were to look at this part, our water has a boiling point of 78 degrees, or sorry, ethanol has a boiling point of 78 degrees Celsius, and water has one of 100. So if we wanted to compare the intermolecular forces, we need more energy to overcome the attractions in the water. We have to go to a higher temperature, which means more energy. So as our temperature increases, our energy is also increasing. And so our intermolecular force must clearly be stronger in water than in ethanol, because we needed more energy there to overcome them. Now for this next part, what I want you to do is I want you to take an HCl. I want you to draw out HCl. And I want you to draw a second one of those molecules to show me how it might interact between those two. So we could have a hydrogen on one side we could have a chlorine on the other. And so if we were adding in a second molecule, we want to think about how they might interact. Now our chlorine, it's got a partial negative there because that bond between hydrogen and chlorine is polar. And so there's some separation there. So we have our hydrogen as being partially positive. We have our chlorine as being partially negative. So when we add in our next HCl, we wouldn't want the chlorine to be on the chlorine side. Those two things would be negative, so they wouldn't really get along. So we might put our chlorine over here, and we could put our hydrogen over here. Now that gives us a partial positive over here, a partial negative. And so if you were to think about how those would interact, we kind of have some attraction here between those two and some attraction here. Let me dash those in a different way. If we added in another chlorine, we might have that chlorine over here, and we might have that hydrogen over here. And you can see how they can start to take on an organization based on these attractions. Now, the way that this is different than the ones that we've been seeing is that these are going to be permanent polarities. And so they lead to a different kind of force. These HCl's are not temporary. They're not because those molecules are moving. So our HCl's, the way that they're interacting is that they have their poles, their partial positive and the partial negative, and so they get attracted between these dipoles to each other. And so we call that our dipole-dipole interaction. And so molecules that have permanent dipoles are attracted to each other. This is the same thing as saying that polar molecules attract other polar molecules. Because they have a positive side and a negative side, then they are attracted to other ones with their positive sides and negative sides. So the positive end of one is attracted to the negative end of the other, and vice versa. But this matters most when the molecules are close to each other. As we move them away from each other, then that strength will drop off in the same way that all of our Coulombic interaction strengths drop off. So you can kind of see that here. This is a measure of our polarity. It's called a dipole moment. So as our dipole moment increases, so does our polarity. The larger the dipole moment is, the more polar. So all of these molecules have a similar size, which means that our London forces are going to be kind of the same. And so as our dipole moment increases, then our boiling point is also increasing. Now, that reminds me that I forgot to mention about how our London forces are kind of attracted to each other. And so our London forces, we talked about them having this temporary dipole. So they're working in a similar way to our dipole-dipole ones. But there's two things that we kind of need to consider with that. One is the size of the dispersion forces. So the magnitude of these dipoles depends on the volume of our electron cloud. The larger the volume, then the more easily it is to polarize one side over the other, right? There's more space, more distance between the electrons, so they can swing more to one side than the other. Shape also has to deal with this for the molecule. The more surface-to-surface contact they have with the other ones, then the more they can trigger dipoles on the other molecule to kind of increase those attractions. And so what we look for our induced one is two things. We're looking for a larger molar mass. The larger the molar mass, the more electrons there are. The larger the electron cloud, the increase the polarizability, and so then the stronger the attractions. So we're kind of going from one side to the other. We want more electrons, and with more electrons, we also want a larger volume, or sorry, a larger electron cloud that they can take up, because we're really just talking about polarizing them. And so a way for us to look at that is kind of like our noble gases. Our noble gases have a similar amount of valence electrons in the sense that they don't have any polarity within them. They exist all by themselves. And we can kind of see their boiling points and how that's tied in with their molar mass. As the molar mass increases for them, the number of electrons increase, and the strength of the dispersion force also increases. So helium has a really low boiling point because it's got very few electrons in there in order to polarize. It's also got a very small size. Xenon, on the other hand, has a much higher boiling point because it's got a much larger molar mass. So when you think about your London forces, you want to tie that directly with your molar mass. If everything is equal, your molar mass is going to separate which one has larger London forces. If one has dipoles and the other one is nonpolar, then that becomes a different part. We'll do that comparison later on. For molecular shape, what you really want is you want long chains as compared to these branched ones. So things that are all clustered together don't give us very strong intermolecular forces. These long chains gives us more interactions between them. If we imagine, if we wanted to stack on the next N-pentane, we could stack it like this, and you would get interaction between each of these molecules, here and here, here and here. On the other hand, on the other side, if I wanted to add in the neopentane, can't really get the same amount of attractions. I can only squeeze so many in because of their shape, right? I can't get these two to line up in the same way I could when they were all a straight chain. Now, the thing that I like about the hydrocarbons is you can really see here the impact that our molar mass has on our boiling point. These are all kind of like a family of molecules. They all look relatively the same. It's a carbon chain going down the middle. So that's like a carbon, a carbon, and a carbon. And they're surrounded with these hydrogens. The only thing that's changing is how long of a chain that is. And that's kind of what they're showing you in this picture. This one has 5 carbons stretched going all the way up to 9. And you can see that as we add more carbons in there, our molar mass goes up. The higher our molar mass, the higher the boiling point. So London forces, that's with all molecules, but primarily we worry about them with our non-polar ones. For our polar molecules, we worry about the dipole-dipole attractions. And so they have the permanent dipole. And so there's always a partially positive and a partial negative side for them to be attracted, just like this. Now, the third type of intermolecular force that we're going to talk about is our hydrogen bonds. And so this is similar to a dipole-dipole, but it's a very special case. So it's a really strong intermolecular force, but it only happens in very certain conditions. So hydrogen is special because hydrogen has 1 electron. So when we bond that with a really electronegative atom, let's say fluorine in this case, when that electron leaves to spend time with this fluorine, the nucleus of that hydrogen is completely exposed. So that means that this proton that's in here doesn't have anything shielding it, so other electrons from a neighboring molecule can get very close to it. This is unique because if we go to the next element that's similar to our hydrogen, our lithium has one valence electron, but it also has two core electrons. And so when this electron gets drawn away towards that fluorine, and so let's say if we like erased it there, that lithium is still protected or shielded by those two core electrons. So it's not the same as the hydrogen where it's got that naked proton exposed. Instead, it's got those core electrons to shield it. So hydrogen's the special case, hence why it gets the name hydrogen bonds. Now, it's not a true bond in the same way as it's not a covalent bond or an ionic bond. It's still just an intermolecular force. It's just very strong. Now, this only works when we can draw that electron far enough away to really expose that proton. And so it only happens with the three most electronegative elements that have a very small size. And that's going to be oxygen, nitrogen, and fluorine. So that top right-hand side of our periodic table. So hydrogen bonds can only occur when a hydrogen atom is directly connected to one. So you have to have a molecule that looks like an O connected with an H, an N connected to an H, or an F connected to an H. If you have a carbon connected to a fluorine and a hydrogen, there's no hydrogen bond because they're too far apart. They have to be directly connected to each other. When they're connected to each other, the very electronegative atom pulls the bonding electrons towards it, and that exposes the nucleus of the hydrogen one, pulling away that, or exposing that proton. And so this is a very strong positive charge attraction for all of the neighboring molecules. So you can kind of see it like this. You can see how skewed that structure gets from that hydrogen bond. Now, molecules can make more than one hydrogen bond, depending on how many things we have attracted. And so an example of this is water. Water has not one hydrogen bond, but two hydrogen bonds. And it's one of the reasons why water has such an extremely high boiling point or melting point for its size. Its molar mass is really small. It's only 18 grams per mole. But because it's got those two hydrogen bonds, it gives it a lot of extra intermolecular force stability there. And so it makes it a much higher bonding or boiling point than we would expect. So these hydrogen bonds are very, very strong. They're stronger than our dipole-dipole and stronger than our London forces. And so if we get a molecule that seems to have a very high boiling point, especially compared to its molar mass, the thing that you want to be looking out for is these hydrogen bonds. Now, while we call them bonds and we talk about them being so strong, to put that in perspective, there's still only about 2 to 5% the strength of a covalent bond. So they are strong for intermolecular forces, but they are not strong compared to those forces holding the molecules to, or holding the hydrogen atom to the oxygen atom inside the molecule. Right? Those covalent bonds are even stronger. Our fourth type of intermolecular force is what we call an ion dipole. So ion dipoles are really important for solutions. And like the name implies, it's going to be the attraction between an ionic substance and the polar solvent. So it's attraction between the ion and then the dipole. So this is from the ionic compound, is the ion. And then the dipole is from our polar covalent compound. So we see this inside of our solutions that get made. Ions from an ionic compound get attracted to the dipole moment. So in this case, this is our chloride. Our chloride is negative, so it's attracted to the partial positive of the H in the water. The sodium, which is positive, gets attracted to the partial negative of the oxygen. And this is what allows for things to dissolve. This attraction, even though an ion-ion is a stronger attraction, because we can get a lot of these ion dipole ones, we might be able to overcome that and we might be able to make the solutions. And so we'll talk about this one a lot in chapter 12. We'll talk about solutions. But for now, what we want to know is that our ion dipole attraction is even stronger than our dipole-dipole and even stronger than our hydrogen bonds. But once again, the intramolecular bonds, so these are the ones between atoms inside the molecule, are much, much stronger than those ones between the molecules. For us to break 1 mole of O to H bonds is about 400 kilojoules. For us to break 1 mole of the hydrogen bonds, it's only about 16. Right? So there's a very big difference in their strengths there. So we'll do some practice problems with this. We want to think about which of these intermolecular forces are stronger than those in O2. Oh, sorry. Why are the intermolecular forces in water stronger than those in O2? And so we want to think about what forces we have present. So we have to classify, are they going to be polar or non-polar? Or is there going to be hydrogen bonds or not? Or are they only going to have London forces? So there's kind of a checklist that you want to walk through. We know they have electrons, so they're going to have London forces. And so to compare London forces, we want to compare our molar mass. We know that our dipoles means that we need polar molecules. And then we would be able to compare the strength of those dipoles if we had the dipole moment for the molecule. So stronger dipole, stronger dipole. And then our last one is going to be hydrogen bonds. And so we need an O connected to an H, an N to an H, or an F to an H for that to happen. So right away, I can tell you that O2 does not have hydrogen bonds because it doesn't have a hydrogen atom. Makes it very hard to have a hydrogen bond if we have that. But other than that, we should look at our Lewis structures. So water is HOH, double bond, O2, double bond. So our water is definitely going to be polar. Our O2 is going to be nonpolar. And so if we wanted to compare their London forces, O2 has stronger London forces than our H2O. Yeah, we can do that. So H2O is not as strong in London forces as our O2 because this one has a higher molar mass. Our dipole, H2O is going to have them. So it's going to be greater than O2's because O2 is nonpolar. So it doesn't have dipole. We also know that hydrogen bonds, water has them, and O2 does not. And so if we wanted to compare our intermolecular forces, even though O2 wins in London forces, our London forces are our weakest forces. It's not until we get to a very large molecule where we have enough London forces to overcome even only a little bit of a dipole. So for our class, you can kind of assume that if you have dipole-dipole forces, you should have a higher boiling point than than a molecule that only has London forces, unless it's like significantly bigger in its size. And so when we talk about significantly bigger, we're talking about molar masses that are probably about 10 times as large. It does depend a little bit on how strong your dipole-dipole is, but that's just a rough rule of thumb. Right? When we compare our CH4 and our H2, if we wanted to think about which one's going to experience stronger London forces, now this question is asking us just for London forces, so we don't even have to worry about dipole-dipoles or hydrogen bonds. We're just looking at London forces. So if we want stronger London forces, we want a higher molar mass. And so CH4 is going to have higher molar mass, so more electrons than our H2, and that's going to give it stronger forces. So in summary, when we're looking for our intermolecular forces, what you're looking for is your molecule polar or nonpolar? If it's nonpolar, then you get the London forces or your dispersion forces. If it's polar, then you can have a dipole-dipole. If there's a hydrogen connected directly to nitrogen, oxygen, or fluorine, then we can have hydrogen bonds. Now, if you have any ions present, so that could be something like a polyatomic ion, or you would have like a very strong or high electronegativity difference between them, then you could have an ion dipole. That could be something like our solutions that we make. Or you could have something like ionic bonding, NaCl, or this one, ammonium nitrate. Those are two polyatomics coming together, making those ions. In terms of strength, right, what you want to think about when you're looking at those factors is which one is a stronger force versus a weaker force, right? So you want to do the interacting molecule. So water is going to be stronger forces than CH4 because it's got things like hydrogen bonds or versus London forces. Then you want to think about the distance between those molecules. The larger the distance apart from them, then the weaker that one is. And so in general, if we can get them closer together, then they're going to feel stronger attractions. And then from there, we have those orientation part. And so we'll talk about these a little bit more in our lecture on Thursday. But that's basically what we're doing with our first part of our intermolecular forces. Now, from here, we can actually get a lot of very interesting parts because our attractive forces impact things like solubility. And so the thing about solubilities are that our molecules, polar molecules attract other polar molecules. And what that means is that we get this statement, like dissolves like. Because of those attractive forces, if we have a partial positive and a partial negative from a polar molecule, it's going to attract other things that have a partial positive and a partial negative. If you're nonpolar, you're not going to be able to compete with those attractive forces, and so you're not going to separate, and you're not going to be dissolved by that solvent. So polar substances dissolve in polar solvents. That means things like water dissolves our ionic compounds because it has because ionic compounds have the positive ions and the negative ions. Something else that's polar is something like methanol or ethanol, and both of those dissolve inside of water because they have that strong dipole-dipole between the oxygen and the hydrogen. Now, nonpolar things dissolve in nonpolar solvents. And so this is why things like oil and water don't mix. Oil is nonpolar and water is polar. And so these two will stay separated. Because of the strong dipole-dipole forces in the water molecules all stick together, and the oil isn't able to kind of get in there to separate them apart. If we had a polar substance, then those attractions could mix in with our water and we would be able to have some solubility or some mixing between them. And so just think that the opposites of the polar molecule attract, and so that's why we get the saying that like dissolves like. So you need polar things to dissolve other polar things. You need nonpolar things to dissolve other nonpolar things. Now this is great if you've ever tried to dissolve something like permanent marker. Permanent marker is generally nonpolar. So it doesn't dissolve well in water. It's why it becomes permanent. And so you could eventually get it out with a lot of soap and a lot of water scrubbing at it. But if you find a nonpolar solvent that you want to use to remove it, so sometimes you can get away with things like isopropanol, which is kind of a mixture of a polar part, but it's got a longer nonpolar side to it. Then we can use that to help get rid of your permanent marker. It's also why if you get it on your skin, if you use a lot of soap, especially if you use like grease cutting soap, you can help remove that permanent marker. So in summary, what we're going to look at is that dispersion forces are the weakest of the intermolecular forces. These also are London forces. They're present in all molecules and atoms because they all have electrons. And all electrons are in motion. And the magnitude of the dispersion forces increases with your molar mass. Polar molecules have dipole-dipole attractions. And dipole-dipole attractions increase with polarity. And so that is going to be your dipole moment. So as your dipole moment goes up, so does your dipole-dipole attractions. Hydrogen bonds are the strongest of the intermolecular forces for a pure substance. And so they're going to be present when you have hydrogen directly connected to an oxygen, a nitrogen, or a fluorine. Ion dipoles, are present in mixtures of ionic compounds with polar molecules. And they are the strongest of these forces that we talked about today. So they are stronger than hydrogen bonds, but you can't really have one compound that has both ions and dipoles. And so that's why hydrogen bonds are generally considered to be the strongest one for a pure substance. And ion dipoles are especially important when we talk about solutions. So we'll get into that in chapter 12. So that's all we're going to cover today. You want to practice going through your compounds, identifying what type of intermolecular forces you have present, and then we'll continue this on Thursday. I'm also going to link you to a video that talks a little bit about chromatography. And that's because chromatography and distillation is one great use of our intermolecular forces and how we can separate compounds from that.